Welcome, dear friend, to Luminous Uplift, a gentle sanctuary where science and wonder meet in the softest of lights. If you have found your way here tonight, perhaps after a long and winding day, know that you are exactly where you are meant to be. Let your shoulders soften, let your breath slow, and allow yourself to simply rest for a little while. Here, we tell stories that uplift the spirit and quiet the mind. Stories born from the deepest truths of our universe, carried to you on a current of stillness and awe. Tonight, we invite you to release the weight of the hours behind you and drift with us across something truly breathtaking, a journey through 13.8 billion years of cosmic history. Imagine traveling backwards through time, sailing gently past the birth of stars and the slow gathering of galaxies through vast luminous clouds of gas and ancient light, all the way to the very first breath of existence itself. These are the peaceful explorations we offer here, quiet voyages through the deep history of everything, tracing the universe's long and luminous unfolding from its earliest whisper to the present moment. If these journeys bring you comfort and wonder, we would love for you to like this video and subscribe so we may continue walking these starlit paths together. No rush, no pressure, simply an open invitation whenever it feels right. Now, let us begin our journey. Close your eyes for a moment if you like. Let your body sink a little deeper into wherever you are resting right now. Feel the weight of the day beginning to lift, slowly, gently, the way a fog burns off a quiet lake in the early morning hours when no one else is watching. There is nothing you need to do right now, nowhere you need to be. You are here, and that is enough. And what I want to tell you about tonight is something so vast, so ancient, and so quietly astonishing that it has a way of making everything feel both infinitely small and infinitely precious at the same time. I want to tell you about the beginning of everything, not just the beginning of the Earth, or the beginning of our solar system, or even the beginning of the stars. I want to take you further back than that, much further. I want to take you to the edge of time itself, to the place where the universe drew its very first breath, to the moment before there were moments. And I want you to hold that thought the way you might hold a smooth, cool stone in the palm of your hand. Just feel the weight of it. Just let it be there. Here is a number that deserves to be spoken softly, the way you might whisper something important to someone you love. The universe is approximately 13.8 billion years old. Say that again, gently to yourself. 13.8 billion years. That number was not guessed, and it was not imagined. It was measured. Scientists discovered it by looking at something called the cosmic microwave background radiation, which is a kind of faint, ancient glow that still fills all of space in every direction. A whisper left over from the earliest moments of creation, like the last trace of warmth on a pillow after someone has risen and walked quietly from the room. By studying the subtle patterns in that glow, the tiny variations in its temperature, scientists were able to read the history of the cosmos the way you might read the rings of a very ancient tree. And what those patterns told us was this: it all began, in some profound and almost unimaginable sense, roughly 13.8 billion years ago. But here's where it gets strange. Here's where the story tilts slightly sideways and asks you to let go of the ordinary way you think about things, not in a frightening way, but in the way a dream sometimes asks you to accept that a door can open into a garden that was not there before, and you simply nod, because in the dream it makes a perfect kind of sense. Before the Big Bang, the concepts of space and time as we understand them simply did not exist. I want you to sit with that for a moment, not to solve it or to fix it, but just to let it rest in your mind like a smooth, quiet stone at the bottom of a still pond. There was no before in any meaningful sense. When we ask what came before the Big Bang, we are asking a question that our language was never built to answer, because the word before implies time, and time itself had not yet been born. It is something like asking what is north of the North Pole. The question sounds reasonable. It has grammar and structure. It follows the usual rules. But when you arrive at the very top of the world, north simply stops being a direction that means anything. You can turn in any direction, and every one of them is south. The question dissolves, not because we are not clever enough to answer it, but because the question itself is reaching beyond the edge of where questions like that can go. So there was no before. There was no dark waiting room where the universe sat patiently until it was ready. There was no void humming with anticipation. There was no ancient silence, because silence requires time, and time did not yet exist. Even the darkness we might imagine was not really darkness in the way we mean it, because darkness is still a place, and there was no place. There was no space. There was no absence of space. There was simply nothing that our minds were ever designed to picture. And yet, something happened, or perhaps more accurately, something began. And the first moment of that beginning, the very first flicker of what we might call existence, was so brief, so impossibly compressed, that it makes every other span of time we have ever conceived feel enormous by comparison. Physicists call it the Planck epoch, and it lasted for what they call Planck time, which is approximately 10 to the negative 43 seconds. That notation, 10 to the negative 43, means a decimal point followed by 42 zeros, and then a 1. It is the smallest meaningful unit of time in all of physics. Below that threshold, our equations stop working. Our mathematics reaches its hand into the dark and finds nothing to hold on to. The laws of physics, as we currently understand them, cannot describe what was happening in that interval, not because the universe was being secretive, but because space and time themselves were so young, so newly knit together, that the very concepts we use to measure and describe reality had not yet settled into their familiar forms. Think of it like the moment just before dawn, when the sky is neither night nor day. There is a quality to that light, or that almost light, that resists being named. You cannot call it dark, but you cannot yet call it bright. It is something in between, something that is only happening right now, in this precise threshold moment, and it will never happen in exactly this way again. The Planck epoch was something like that. But stranger, it was the threshold moment of all threshold moments, the one from which all subsequent moments would eventually flow. And what existed in that moment? What filled that impossible first flicker of time? Everything. All of it. Every single atom that would ever become a star, every molecule that would ever become a flower, every particle that would ever drift through the bloodstream of a living creature, every photon that would ever travel for billions of years across the emptiness of space to land finally on a sleeping planet and warm the face of someone lying in a sunlit field. All of that. All the matter and energy in the entire observable universe was compressed into a region smaller than a single proton, smaller than the nucleus of a single atom, smaller than anything you could ever see under a microscope or hold in your hand or gesture toward with a pointing finger. The word small does not begin to describe it. The word infinite does not begin to describe the density of it. It was a point of such profound compression that it existed almost outside of description, outside of metaphor, outside of the reach of ordinary wondering. And then it expanded. But here is the part that so many people misunderstand, and I want to offer it to you gently, like a small and quiet correction given with great tenderness. The Big Bang was not an explosion in space. It was not like a bomb going off in the middle of a room, flinging pieces of itself outward into an emptiness that was already there waiting to receive them. There was no room. There was no emptiness. There was no outside. The Big Bang was an expansion of space itself, of the very fabric of reality, and it did not happen in a location. It happened everywhere, simultaneously. Every point in what would become the universe was the center of the expansion, because the expansion was not something that space was doing from some particular place outward. It was something that space was doing within itself, everywhere at once, as if the idea of distance itself was being invented in real time, as if the very concept of here and there was being written for the first time by a hand that had never held a pen before. Picture it, if you can, as the surface of a balloon being inflated. If you drew dots on that surface and then blew air into the balloon, every dot would move away from every other dot. No single dot is the center of the expansion. No single dot is the origin point. The expansion is happening in the fabric itself, and every point on that fabric is equally valid, equally original, equally ancient. Now, remove the balloon entirely. Remove the idea that there is an inside or an outside. Remove the idea that the surface is a surface of something that is closer to what happened. Space itself was growing from nothing into something, and every part of it was the beginning. How do we know all of this? How did we arrive at this picture? It came slowly, the way most great understandings come, through accumulation and patience and the willingness to follow the evidence wherever it led, even when it led somewhere strange. Edwin Hubble, looking through his telescope in the 1920s, noticed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. The universe was expanding. If it was expanding now, then it must have been smaller in the past. Trace that expansion backward in time, and you arrive inevitably at a moment of origin, a beginning. And then later, in 1964, two radio astronomers named Arno Penzias and Robert Wilson detected a faint uniform hiss of microwave radiation coming from every direction in the sky. A signal they initially thought was interference, perhaps from pigeon droppings inside their antenna. But it was not interference. It was the oldest light in the universe. It was the cosmic microwave background, that primordial glow left over from the Big Bang itself, still traveling, still present, still filling every corner of space after 13.8 billion years. It was the universe's own memory of its first moment of heat and light, and it was whispering to us from across the entirety of time. There is something in that image that I find deeply, quietly moving, that we live inside a universe that carries its own earliest memory everywhere within it. That you, right now, lying still and letting your breath slow, are surrounded by the faint afterglow of creation. Those ancient microwaves are passing through the walls of wherever you are. They are moving through the air around your body, through the very atoms of your skin and bones, and the soft tissue of your dreaming mind. They have been traveling since almost the very beginning, and they will keep traveling long after every star has gone cold, a gentle and eternal signal that something once happened, that existence once ignited, that time itself once had a birthday. 13.8 billion years ago, something began. It began from a state so compressed, so singular, so far outside the reach of ordinary imagination that we can only approach it sideways. Through mathematics and metaphor and the quiet willingness to stand at the edge of understanding and simply look out into the dark without flinching. It began not in a place but as a place, not in time but as time. It was not an event that happened to the universe. It was the universe in the very act of beginning to be itself. And in that beginning, everything that would ever exist was already there in some form, folded impossibly small, trembling on the threshold of becoming. And we are made of that beginning. Every atom in your body was forged in the hearts of ancient stars, and those stars were made of gas, and that gas condensed from the early universe. And the early universe grew from that first impossible moment of expansion. You are not separate from the origin. You are the origin, continuing. You are the universe, having taken 13.8 billion years to arrive at the particular and beautiful form of you. Lying here now in the quiet, breathing slowly, letting the weight of ordinary things fall gently away. The story of where all of this came from is not a cold or clinical story. It is one of the most intimate stories ever told. It is the story of how something came from what we can barely call nothing, of how time invented itself, of how space learned to expand, of how matter and energy and light and warmth and eventually consciousness all grew from a single point of inconceivable smallness, like a flower unfolding in slow motion across billions of years, opening one petal at a time. Each petal a galaxy, each galaxy a universe of its own, and all of it breathing outward still, even now, even tonight, even in this soft and drowsy moment. Even as your eyes grow heavy and the world outside goes quiet, and in that first impossible breath of existence, something that would one day become light began to stir, not yet as photons or warmth or color, but as a pure, trembling potential coiled within the fabric of a universe that was only just learning, and in that first impossible breath of existence, something that would one day become light began to stir, not yet as photons or warmth or color, but as a pure, trembling potential coiled within the fabric of a universe that was only just learning how to be a universe at all. Close your eyes for a moment and try to imagine it, if you can. Not darkness, because darkness requires the absence of something, and in those first unimaginably early moments there was no absence anywhere. Everything was presence. Everything was heat and motion, and density so extreme that the very concept of emptiness had not yet been invented by the cosmos. There was no space to stand in, no air to breathe, no ground beneath anything. There was only the churning, the seething, the incomprehensible intimacy of a universe so small and so hot that all the matter and energy that would one day become galaxies and oceans and sleeping children was pressed together into something almost unthinkably compact. And yet, even then, there was already a kind of order trying to emerge. Even in those first wild moments, the universe was not merely chaos. It was chaos with rules, chaos with mathematics humming quietly underneath it, like a lullaby that the cosmos was singing to itself. In the very first microsecond, a single millionth of 1 second after everything began, the universe existed as something physicists call a quark gluon plasma. It is a beautiful and strange name for a beautiful and strange thing, and it describes a state of matter so exotic that we have only ever glimpsed hints of it in the most powerful particle accelerators ever built by human hands. In that state, the fundamental building blocks that would one day compose all the matter you have ever touched, all the matter that has ever existed anywhere in the observable universe, those tiny pieces called quarks were not yet bound together. They roamed freely through the hot, dense soup of the early cosmos, swimming in a sea of their own making, carried along by the particles that would one day hold them together, the gluons, which were themselves part of the churning, the flowing, the everything of that first impossible moment. Think of it this way, as gently as you can, letting the image drift through your mind without holding it too tightly. Imagine the universe in those first moments as something like an ocean of inconceivable heat, not an ocean you could sail across or dive into, but an ocean in the sense of something vast and fluid and alive with motion at every scale, something that moved in ways that nothing else in all of later history would ever quite move again. And within that ocean, the quarks moved freely, tumbling and flowing, not yet gathered into the protons and neutrons that would one day anchor the atoms of every living thing. But the universe was expanding. It had been expanding since the very first moment of its existence, reaching outward in every direction simultaneously, not into anything, because there was no outside to expand into, but simply becoming larger, becoming less dense, becoming cooler. And cooling, it turns out, changes everything. As the temperature dropped, as that first microsecond stretched into the next, and the universe grew even slightly less ferociously hot, something began to change in that primordial ocean. The quarks, which had been moving freely through the plasma, began to feel the pull of those gluon forces more strongly. The cooling allowed those forces to take hold in a new way, and slowly, tenderly, inevitably quarks began to bind together. 3 quarks would find each other in that seething soup, would be drawn together by the strong nuclear force, one of nature's 4 fundamental forces. And in binding together, they would become something new. They would become protons and neutrons, the first composite particles, the first objects in the universe that were built from smaller pieces. A proton. It is such a small thing to contemplate, and yet it is worth pausing here, in the quiet of wherever you are, to feel the extraordinary weight of what that means. Every proton in every atom of your body is directly descended from those first protons that formed in the early universe. The proton at the heart of every hydrogen atom in your blood, in the water you drank today, in the tears you have cried and the rain that has ever fallen on your face. Those protons were born in the first fractions of a second after the universe began. They are among the oldest things that exist. They have been protons for longer than stars have been stars, longer than galaxies have had their shapes, longer than any planet has circled any sun anywhere. And neutrons formed alongside them, the slightly heavier cousins, the particles without charge, the quiet ones that would later play their own essential role in holding atomic nuclei together. Protons and neutrons emerging together from that cooling quark gluon plasma, settling like the first sediment in a primordial sea, the universe already becoming something more structured, something with a little more architecture, even if that architecture was still almost incomprehensibly simple compared to what would one day grow from it. But here, in the story of those first minutes, there is a detail so quietly astonishing that it deserves to rest in your mind for a moment before you let yourself drift further towards sleep. When the universe began, it created matter and antimatter in almost equal proportions. For every particle of matter that sprang into existence, there was a corresponding particle of antimatter, its mirror image, its opposite in charge and in certain fundamental properties. And when matter and antimatter meet, they annihilate each other, converting entirely into pure energy, into radiation, into light. So by all the mathematics of a perfectly symmetric universe, there should have been nothing left. Matter and antimatter should have destroyed each other completely, and the universe should have been nothing more than a vast sea of radiation, cold and featureless and empty of any particle at all. No protons, no neutrons, no atoms, no stars, no you. But the universe was not perfectly symmetric. In some subtle, profound, and still not entirely understood way, the cosmos had a slight preference for matter over antimatter, not a large preference, not anything dramatic or obvious. For every billion particles of antimatter that were created, there were 1,000,000,001 particles of matter. One extra particle for every billion pairs, a tiny asymmetry, a whisper of imbalance, so small it seems almost like a rounding error in the mathematics of creation. And yet that tiny imbalance is the reason everything exists. When the great annihilation happened, when matter and antimatter destroyed each other in an event that released unimaginable amounts of energy as radiation, those 1 in a billion survivors remained. The leftover matter, that slight excess, that infinitesimal asymmetry, became every proton, every neutron, every atom, every molecule, every planet, every ocean, every living thing that has ever been. You are made of leftovers. The entire observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, is the residue of that 1 in a billion surplus. It is perhaps the most humbling and the most wonderful fact in all of science that we exist because of a rounding error, because of a slight imperfection in the symmetry of the early cosmos. Let that settle quietly for a moment. You are here because the universe was just barely imperfect in exactly the right way. Now, the universe continued to cool. Time was passing, though time in those early moments moved in a different relationship to everything than the time you know. Seconds stretched. A second in the early universe contained more change, more transformation, more fundamental physics than entire centuries would later contain. The universe was learning fast, changing fast, settling into its nature fast. And as the first second gave way to the first minute to the second and the third, the cosmos was growing quieter in its violence, lower in its temperature, wider in its reach. At these temperatures still, millions of degrees, but falling, always falling, the protons and neutrons that had formed from the quark-gluon plasma began to interact with each other in a new way. The universe was still too hot for electrons to settle into orbits around nuclei, still too hot for anything we would recognize as an atom to form. But it had cooled enough that something else could happen. Protons and neutrons could begin to fuse. This is the process called Big Bang nucleosynthesis, and it is one of the most beautiful things that physics has ever described. Nucleosynthesis means, quite simply, the making of nuclei, the forging of the first atomic cores. In the first 3 minutes of the universe's existence, in those brief moments before the cosmos had cooled too much for fusion to continue, protons and neutrons combined with each other to form the first nuclei. A proton and a neutron binding together became deuterium, heavy hydrogen, one of the earliest steps in the chain. Deuterium nuclei combined further to form helium. Other light elements formed in tiny traces, and the universe, in the space of those 3 minutes, wrote the first chemical recipe for all the matter that would ever exist. When those 3 minutes were over, when the temperature had dropped below the threshold at which nucleosynthesis could continue, the proportions had been set. Roughly 3/4 of all the ordinary matter in the universe by mass was hydrogen. Roughly 1/4 was helium. Small traces of other light elements like lithium rounded out the recipe. And those proportions, established in the first 3 minutes of time, are still observable today. When astronomers look at the oldest stars, the most ancient objects in the universe, stars that formed when the cosmos was very young from the primordial gas that filled it, they find those same proportions. 75% hydrogen, 25% helium. The fingerprints of those first 3 minutes, preserved across all of time, written into the composition of the oldest light that reaches our telescopes. It is as though the universe signed its name in those first moments, wrote a recipe on the fabric of existence itself, and every star that has ever burned, every galaxy that has ever formed, every planet that has ever cooled from hot gas into solid ground has carried that signature forward. And through all of this, through the cooling and the fusion and the forging of those first nuclei, the universe remained opaque. This is perhaps a strange thing to contemplate in a quiet way, as you let yourself grow sleepy. We think of space as something you can see across, something transparent, something through which light can travel freely for billions of years to reach our eyes or our telescopes. But in those early moments, the universe was not like that at all. The energy density was so extreme, the plasma so thick with charged particles, that light could not travel freely. Photons, the particles of light, were constantly scattering, constantly bouncing off the charged particles that filled the cosmos, unable to travel more than a tiny distance before being deflected again. The early universe was opaque. It was like standing inside the core of a star, where light is so intensely scattered that a photon generated in the sun's center takes tens of thousands of years to random walk its way to the surface, bouncing and scattering and being absorbed and re-emitted endlessly. The early universe was like that, but everywhere at once, in every direction, at every point in space, the cosmos was a fog of such density and heat that light was trapped within it, unable to escape, unable to carry information across any meaningful distance. The universe was full of light, and yet, in a certain sense, completely dark to any observer, because that light could not travel far enough to be seen. There is something almost dreamlike about that image, isn't there? A universe blazing with energy, saturated with light, and yet utterly opaque, a cosmos so full that nothing could pass through it. Like a thought that is so dense with meaning that it cannot quite be spoken yet, a universe that had not yet learned how to let itself be seen. The hydrogen and helium nuclei drifted in that luminous fog, suspended in a sea of electrons and radiation, all of it still too hot and too dense for anything more to happen for quite a while yet. The universe needed time. It needed hundreds of thousands of years of slow, patient cooling before those electrons would finally be able to settle around those nuclei and form the first complete atoms, before the fog would finally clear and light would finally be free to travel, and the cosmos would at last become transparent. But that is a story for a little later. For now, rest with the image of those first 3 minutes, the quark soup cooling into protons and neutrons, the protons and neutrons finding each other to forge the first nuclei. the slight asymmetry between matter and antimatter, giving the universe its only chance at having any substance at all, the proportions of hydrogen and helium being fixed for all of time in those brief, ancient, elemental moments. Rest with the knowledge that the universe was already, in those first minutes, doing something that can only be described as extraordinary. It was building from the simplest possible ingredients, from the most fundamental pieces of matter, from a recipe written in the language of temperature and time. It was building toward everything that would ever be. Not yet stars, not yet planets, not yet life or thought or sleep or dreaming. But the ingredients were there, quietly settling into place, waiting with the patience of physics for what would come next. And think, if it does not chase away your sleep to think it, how extraordinary it is to consider that every hydrogen atom in your body, every molecule of water that has ever passed your lips, was forged in those first trembling minutes, carried forward across all the intervening ages, as tenderly as how extraordinary it is to consider that every hydrogen atom in your body, every molecule of water that has ever passed your lips, was forged in those first trembling minutes, carried forward across all the intervening ages, as tenderly as a flame passed between cupped hands. In a dark corridor, never extinguished, never truly lost, only transformed and carried onward through the long patience of time. And what a time it was becoming. What a slow and enormous unfolding was already underway. Though no eye existed yet to witness it, no mind to marvel, no heart to feel the strange and overwhelming beauty of a universe learning, gradually, quietly, how to be itself. Let us rest here for a moment in the story, the way you might pause at a window on a clear night and simply breathe, simply look before moving on. Because what comes next in the history of everything is something so profound, so deeply hushed, that it deserves to be approached with gentleness, with the kind of reverent quiet you might feel standing at the edge of something vast, an ocean in the dark, a forest at midnight, a room where something sacred has recently happened. The universe in those earliest chapters we have already visited together was a place of extraordinary heat and noise. Plasma and light locked together in a kind of intimate, churning conversation, photons endlessly colliding with charged particles unable to travel freely. Unable to carry information anywhere because everywhere was equally, brilliantly, frantically opaque. Imagine a fog so thick and luminous that even light itself could not navigate it, could not find a way through, could only ricochet and scatter and ricochet again, trapped in a perpetual dance of collision and redirection. This went on for a very long time by the standards of a young universe. 380,000 years. 380,000 years of this radiant, impenetrable fog. The universe cooling all the while, degree by patient degree, the way a stone left outside on an autumn evening slowly releases the warmth it gathered from the afternoon sun, slowly, slowly, slowly releasing it, growing quieter, cooling into something new. And then at a threshold so precise that cosmologists speak of it almost with reverence, something extraordinary happened. Something that seems, from our vantage point, across all the billions of intervening years, almost impossibly elegant. The universe cooled to a temperature of roughly 3,000 Kelvin, and at that temperature something became possible that had never been possible before. Electrons, those restless, negatively charged particles that had spent 380,000 years moving freely through the plasma, began to slow enough, to settle enough, to be captured, to be gently claimed. The protons, the nuclei of hydrogen atoms, reached out across the narrowing distances and gathered their electrons in. The electrical attraction that had always existed between them, but had always been overwhelmed by the furious thermal energy of the plasma, was finally gently sufficient. And one by one, across the entire vast expanse of the cosmos, hydrogen atoms became whole, became neutral, became complete. This event is called recombination, which is perhaps a slightly misleading name, since the electrons and nuclei had never actually been combined before in the history of the universe. They were combining for the very first time, but the name has stayed, carried forward like so many things in science, a fossil of earlier thinking embedded in the language we still use today. What recombination gave to the universe was something so simple and so fundamental that it is almost difficult to articulate without losing its magnitude. It gave the universe transparency. Before recombination, light could not travel, not freely, not anywhere. The universe was a room with no windows and walls, made of light itself, everything bouncing off everything else in an endless luminous confusion. But the moment those electrons settled into their orbits around those protons, the moment neutral hydrogen formed across the cosmos, the universe simply opened. Like eyes opening, like a fog lifting on a still morning to reveal a landscape that was always there waiting. The photons, freed at last, began to travel. In every direction, simultaneously across a universe that had suddenly become transparent, they streamed outward. They have been traveling ever since. They are still traveling now. They are reaching us at this very moment from every direction, from every point on the sky, the oldest light in the universe, light that has been in motion for 13.8 billion years. Light that carries within it the fingerprint of the universe at that one precise and extraordinary moment. We call it the cosmic microwave background radiation. And it is, in the most literal sense imaginable, a portrait, a photograph taken of the universe at the moment it first became possible to take a photograph of the universe, the oldest image that exists or can ever exist, encoded not on paper or glass or digital sensor, but in the fabric of the cosmos itself, written in the wavelengths of ancient light that have stretched and cooled as the universe expanded, redshifted now from the warmth of visible light down into the quiet frequencies of microwaves, but still present, still arriving, still carrying that original message across all the years. When cosmologists study the cosmic microwave background, they are looking at the universe in its infancy. They are seeing the actual texture of that moment, the tiny fluctuations in temperature and density, the gentle ripples in the fog at the instant the fog lifted. And in those ripples, those almost imperceptible variations of 1 part in 100,000, they can read the seeds of everything that came after. Every galaxy, every star, every world, every moment of life and thought and dreaming that the universe would eventually produce. All of it, written in that ancient light, waiting patiently across the billions of years to be read. But here's where the story does something unexpected. Here's where the universe, newly transparent, newly quiet, having just performed this miracle of becoming visible for the first time, does something that seems almost counterintuitive. Something that requires a particular kind of patience to appreciate. Having just become bright with the release of all that recombination light, the universe went dark. Not gradually, not subtly, completely. There were no stars yet. There were no galaxies. There were no nebulae glowing in the light of young suns, no supernovae blazing for brief, brilliant moments across millions of light years. There was nothing that made light. There was only the cooling, expanding, deepening dark of an enormous and ancient space filled with hydrogen and helium gas, growing quieter and colder and more diffuse with every passing moment. The recombination light itself stretching away into longer and longer wavelengths as the universe expanded, shifting from visible light into infrared, from infrared into wavelengths too long for any eye to perceive, leaving behind a darkness more complete than anything we can imagine from our sun-warmed, star-filled vantage point on this small blue world. This period in the history of the universe is known, and the name is perfect, as the Cosmic Dark Ages. It lasted, by current estimates, from roughly 150 million years after the Big Bang to somewhere around 800 million years after. 650 million years of darkness. 650 million years of a universe that contained everything necessary for the eventual emergence of galaxies and stars and planets and life, and yet produced none of it. Simply drifted, simply cooled, simply waited, in the way that seeds wait through a winter that seems to have no end, in the way that the ground waits beneath the snow, patient and full and quietly preparing. There is something I find extraordinarily moving about the Cosmic Dark Ages, something that I hope you might feel too as you lie there in your own small darkness, in the warm gravity of your bed. Listening to these words drift past you like clouds on a still night. There is something moving about a universe so vast and so ancient, sitting in the dark without any light of its own, filled with the slow music of gravity and the drift of gas clouds and the patient accumulation of what would become the first structures, the first gatherings, the first tentative organizations of matter reaching toward something, though it did not yet know what, because something was happening in that darkness. The darkness was not empty. The darkness was not idle. Gravity was working, as it always works, quietly and without announcement, drawing matter toward matter across distances that stagger the imagination. The hydrogen and helium gas that filled the universe was not perfectly uniform. It had those tiny ripples in it, those fluctuations that we can still read in the cosmic microwave background, those almost imperceptible variations in density that had been written into the universe in its earliest moments. And those variations, those places where the gas was very slightly denser than the surrounding average, became gravitational seeds. The slightly denser regions pulled on the gas around them, pulled gently at first, with the patience of something that has all of time available to it. And the gas responded, as gas always responds to gravity, by drifting, by accumulating, by gathering in its slow and liquid way toward those seeds of greater density. The universe was organizing itself in the dark, writing the outlines of its future in the invisible language of gravitational attraction, drawing the first sketches of what would eventually become the cosmic web, the vast and intricate network of filaments and voids and clusters that gives the large-scale structure of the universe its extraordinary foam-like, almost biological appearance. And then, after all those hundreds of millions of years of patient, lightless preparation, something happened that changed the universe forever. Something small by cosmic standards, and yet of almost incomprehensible significance. In regions where the gas had grown dense enough, where the accumulated mass had grown sufficient, where the inward pressure of gravity had finally overcome the outward pressure of the gas resisting compression, the first stars were born. The very first stars. Try if you can, to hold this image in your mind as gently as you would hold something fragile. A universe that has been entirely dark for hundreds of millions of years. Vast, cold, silent, and then in one place, and then another, separated by distances of millions of light years, a light appears. Not the warm, familiar light of our sun, which is itself a second or third or fourth generation star built from materials that previous stars had created and scattered. No, these first lights were something stranger and more primordial than that. They are called population 3 stars, and everything we know about them, or can theorize about them, suggests they were extraordinary beyond ordinary comprehension. They formed from pure hydrogen and helium, those two elements that the Big Bang had made, because those were the only elements that existed. There were no heavier elements yet. No carbon, no oxygen, no nitrogen, no iron, no silicon. The periodic table, that remarkable catalog of everything that matter can be, existed at that moment as only its first 2 entries. Everything else had yet to be made. And because there were no heavier elements to absorb energy and cool the gas clouds as they collapsed, the gas clouds grew very hot as they contracted, and they kept contracting, and they kept growing hotter, and they accumulated into objects of extraordinary mass. The estimates vary, because we have never directly observed a population 3 star, but the calculations suggest they may have been hundreds of times more massive than our own sun. Some models suggest they could have been even larger than that. They were monsters by stellar standards, luminous beyond anything our solar system has ever hosted, burning through their fuel at a rate that made their lives not the comfortable billions of years our sun enjoys, but perhaps only a few million years, perhaps only a few 100,000. By cosmic timescales, they were like mayflies, like the brief, brilliant lives of flowers that bloom for a single day and then are gone. But what they did in their brief, blazing lives, and what they did in their deaths, was nothing less than the creation of chemistry itself. Deep in their cores, under pressures and temperatures that our minds can approach only through mathematics and imagination, hydrogen was fused into helium, helium was fused into carbon, carbon into oxygen, oxygen through successive stages of fusion into neon, magnesium, silicon, sulfur, and finally iron. Iron? That strange final element that even the most massive stars cannot usefully burn, that accumulates in the stellar core like a kind of cosmic debt that eventually falls due all at once. When the iron core of one of these vast first stars grew too large to support its own weight, the collapse was catastrophic and immediate, and the resulting explosion, the supernova, was so violent and so brilliant that for a brief moment a single dying star outshone every other thing in the universe combined. And in that explosion, in that final act of extraordinary violence and extraordinary generosity, all those heavier elements that had been forged so patiently in the stellar interior were released, scattered outward into the surrounding space, seeded into the gas clouds that drifted through the darkness between the first proto-galaxies. The universe, through the deaths of its first stars, received the gift of chemistry. Every element heavier than helium that has ever existed anywhere in the cosmos was made in a star, was scattered by a stellar death, was carried on the slow currents of space and time to the places where new stars and their worlds would eventually form. The calcium in your bones, the iron in your blood, the oxygen in every breath you take, the carbon that is the backbone of every molecule in every cell of your body, all of it, star-forged. All of it, born in those first extraordinary fires and scattered through the cosmos in those first extraordinary deaths. And so the story of those first stars is not only a story of light appearing in darkness, though it is certainly that, it is also the story of the universe discovering for the first time what else it could make, the story of matter learning that it could become something more than hydrogen and helium, could become the astonishing diversity of elements that makes a rocky planet possible. That makes an ocean possible. That makes a living cell possible. That makes this moment, this quiet moment of you resting and listening, possible. The first stars lit the darkness, and then they died, and in dying they made everything. They made the conditions for everything. They left behind enriched gas clouds and the slowly cooling remnants of their cores, neutron stars and black holes, collapsed objects of unimaginable density, sitting quietly in the dark, holding within themselves the compressed memory of all that heat and light and nuclear creation. And so the darkness was not empty but full of slow gravitational dreaming, hydrogen clouds drifting together across millions of light years, drawn by invisible threads of gravity into the first gentle gatherings that would become over countless patient millennia. And so the darkness was not empty but full of slow gravitational dreaming. Hydrogen clouds drifting together across millions of light years, drawn by invisible threads of gravity into the first gentle gatherings that would become over countless patient millennia. The luminous islands we call galaxies, those slow-spinning cities of stars that now populate every corner of the observable universe like embers scattered across an endless dark hearth. Close your eyes for a moment if you like, and imagine yourself impossibly high, higher than any mountain, higher than any cloud, higher even than the orbit of satellites. Imagine you are rising still, up and up through the thin, cold dark between worlds, past the slow wandering planets, past the edge of the solar system, where the sun becomes just another star among stars. Imagine rising further, impossibly further, until the Milky Way itself falls away beneath you in a soft, luminous spiral, and then further still until even that great wheel of light becomes small, becomes a single point among countless other points. Now imagine you can see all of it at once, the full architecture of everything that exists, and you're looking down at it the way a traveler in an airplane looks down at a city at night, seeing the golden traceries of streets and neighborhoods spread across the dark earth below. And then the thought arrives, as gently as a dream arriving. Each of those lights is not a street lamp, not a window, not a single modest flame. Each of those lights is itself a city of 100 billion suns. That is what it is to understand a galaxy, and the universe is full of them. The story of how they came to be is one of the quietest and most patient stories in all of nature. It begins, as so many things begin, in the aftermath of the Big Bang, in that primordial era when the universe was still young and hot and restless. In the first few 100,000 years, matter and energy were locked together in a brilliant plasma, a glowing fog so dense that light could not travel freely through it. But as the universe expanded and cooled, as it always does when given enough time and space, something remarkable happened. The fog began to clear. Electrons settled into orbit around atomic nuclei, forming the first atoms, mostly hydrogen, with a generous helping of helium and traces of a few other light elements. And for the first time, light could travel freely, streaming outward in all directions, carrying with it a faint imprint of the temperature variations that rippled through that. Early plasma-like patterns in cooling porridge. Those temperature variations, those faint ripples, were the seeds of everything. They represented tiny differences in density, regions where matter was, by the smallest of margins, slightly more concentrated than average. And where there is slightly more mass, there is slightly more gravity. And gravity, as you know by now, is patient. It does not hurry. It simply pulls steadily and without rest across whatever distances it must cross for whatever time is required. Into this quiet work stepped the great invisible architect of the cosmos, dark matter. Now, dark matter does not glow. It does not emit light or absorb it. It does not interact with the electromagnetic force that governs so much of the ordinary world. If you reached out your hand right now, dark matter would pass through it like a ghost through a wall, leaving no trace of its passage. And yet it is everywhere. It fills the universe with its quiet, massive presence, making up approximately 27% of the universe's total energy content, more than 5 times the mass of all the ordinary. Visible matter combined. All the stars, all the planets, all the gas and dust and swirling nebulae that fill our nights with beauty, all of that accounts for less than 5% of what exists. The rest is dark matter and the even stranger dark energy. But for now, in this chapter of the story, it is dark matter that commands our gentle attention. Dark matter clustered first, before the stars had switched on, before the first atom of hydrogen had fused into helium inside any stellar core. Dark matter was already gathering itself into vast invisible halos and filaments, sculpting the large-scale architecture of the universe with the slow and certain authority of gravity. Where dark matter accumulated, it deepened the gravitational wells that ordinary matter, gas, mostly hydrogen drifting in the dark, would eventually fall into. The gas followed the dark matter the way water follows the contours of a landscape, pooling in valleys, flowing along channels, collecting wherever the invisible terrain dipped deepest. Within the first billion years after the Big Bang, those collections of gas became dense enough and cool enough to begin collapsing under their own weight. And as the gas collapsed, as it fell inward along those dark matter halos, it began to fragment, to break into smaller clumps, each clump falling further inward, heating as it compressed, until at the hearts of the densest regions, temperatures rose high enough for nuclear fusion to ignite, and the first stars were born, enormous, brilliant, burning through their fuel at extraordinary speed. But around and beyond those first stars, the larger process continued. The gas, the dark matter, the growing collections of young stars, all of it was assembling itself slowly and irresistibly into the first galaxies. These early galaxies were smaller and less orderly than the great spirals and ellipticals we see in the universe today. They were irregular, turbulent things, rich with young blue stars and churning gas, colliding and merging with one another in the crowded early universe the way foam gathers and combines on the surface of a gently stirred cup. Gravity does not only pull things downward in isolation, it draws things together across space, bridging distances that seem impossibly vast by our terrestrial standards, but are, on cosmic timescales, quite intimate. And so the small gathered into the larger gathered further still. Over billions of years, through countless mergers and accretions and slow gravitational dances, the galaxies we see today took shape. This process of merging and growing, is not a relic of the ancient past. It is ongoing. It is, in fact, one of the primary drivers of galactic evolution, a fact as strange and beautiful as anything in science. The galaxy you live inside, the Milky Way, that soft, luminous band you can sometimes see stretched across a dark summer sky, is itself a product of mergers. Over its long history, stretching back nearly as far as the universe itself, the Milky Way has absorbed dozens of smaller galaxies, drawing them in with its gravity, shredding them gently apart with tidal forces, incorporating their stars and gas and dark matter into its own growing body. There are streams of stars in the Milky Way's halo right now, long, curving rivers of suns that are the remnants of smaller galaxies consumed long ago. Their forms stretched and dissolved into new shapes by the gentle violence of gravitational absorption. We contain multitudes in the most literal astronomical sense. The Milky Way itself, in its current form, is a grand and humbling thing. It spans roughly 100,000 light years from edge to edge, a distance so vast that light itself, traveling at almost 300,000 kilometers per second, would take 100,000 years to cross it. Within that span, live somewhere between 100 and 400 billion stars. 100 billion, at the very least. Perhaps 400 billion. We cannot count them precisely. There are too many, and much of the galaxy is obscured by dust. But even the lower estimate staggers the imagination. If you tried to count one star per second without stopping, without sleeping, it would take you more than 3,000 years to reach a billion. You would need over 300,000 years to count them all. And the Milky Way, for all its grandeur, is not alone. It is part of what astronomers call the local group, a gravitationally bound collection of more than 50 galaxies of various sizes from the majestic Andromeda galaxy, which is even larger than our own Milky Way, to a collection of smaller, irregular galaxies and dwarf galaxies that cluster around the larger ones like children gathered close to their parents. The large and small Magellanic Clouds, visible from the southern hemisphere as detached wisps of the Milky Way, are two of these smaller companions. Their fates intertwined with ours across incomprehensible stretches of time. And speaking of intertwined fates, there is a collision coming. It is not imminent by any human measure, and there is no reason for anything resembling alarm, but in approximately 4.5 billion years, the Milky Way and the Andromeda galaxy will meet. They are already approaching each other. Right now, at this moment, as you lie resting and the world outside turns slowly in its sleep, Andromeda is moving toward us at roughly 110 kilometers per second. That sounds fast, and it is fast by any standard we use in daily life. But the distances involved are so enormous. Andromeda is currently about 2.5 million light years away, that the encounter lies impossibly far in the future, beyond the lifespan of the Sun's current stable phase, beyond almost anything we might comfortably imagine. When the merger does occur, it will be like all galaxy mergers, a surprisingly gentle affair in terms of direct collisions. Stars are so small relative to the distances between them that even as two galaxies interpenetrate and merge, the individual stars almost never collide directly. Instead, what happens is a vast gravitational reshaping. Stars are flung into new orbits. Spiral arms are disrupted. Vast waves of gas compression trigger enormous bursts of new star formation, lighting the merged galaxy with brilliant blue fire. The two galaxies will pass through each other, drift apart, fall back together again, and over hundreds of millions of years, slowly settle into a single new elliptical galaxy, sometimes informally called Milky Way, a name with a certain dreamy poetry to it. The Sun, if it still exists, will most likely be swept into a new orbit within this new merged galaxy. But the Earth, if it still orbits the Sun, will be perfectly safe, adrift in a new galaxy. Yes, changed in ways we cannot fully imagine. Yes, but safe in the vast, gentle, star-salted dark. Zoom out now. Zoom out far beyond the local group, beyond even the Virgo supercluster, of which our local group is a tiny part, and what emerges is a structure of breathtaking scale and intricacy. The universe on its largest scales is not a uniform fog of galaxies distributed evenly in every direction. It is instead a cosmic web, a vast three-dimensional lacework of filaments and sheets and nodes with enormous empty regions called voids stretching between them. The filaments are made of dark matter and gas, and along them, like beads along a thread, the galaxy clusters gather. Where multiple filaments intersect, the largest structures in the universe emerge, superclusters, vast gravitational knots containing hundreds or thousands of galaxies. And between them, the voids, regions nearly empty of galaxies, spanning hundreds of millions of light years, dark and quiet and almost incomprehensibly large. This cosmic web began as those tiny temperature variations in the early universe. Those faint ripples we mentioned, the seeds planted in the first moments. Gravity amplified those seeds over billions of years, drawing matter toward the denser regions, draining the voids, building the filaments thicker and the nodes more crowded. The same process that drew hydrogen into the first stars drew those stars into galaxies, and those galaxies into clusters, and those clusters into superclusters, all at every scale. The same patient gravitational logic, the same slow dreaming. The voids are not entirely empty. There are solitary galaxies even in the deeps between the filaments, wanderers, outcasts, island universes, so remote from their nearest neighbors that they may never merge with anything. Their long futures unfolding in a profound and peculiar solitude. But they are rare. Most galaxies know the company of others, feel the gravitational whisper of neighbors near and far, are embedded in the great web that structures all of space. When astronomers map the large-scale structure of the universe, when they plot the positions of millions of galaxies in 3 dimensions, what appears on their screens resembles something organic, something alive, a vast neural network, or the inside of a soap foam, or the microscopic structure of bone. The same patterns appear at wildly different scales throughout nature, a deep geometric resonance that speaks to something fundamental about how matter and gravity and time work together. The universe, it turns out, has a shape, a texture, a filigree, visible only from the greatest distances, woven by nothing more than time and gravity and the slow, luminous patience of gas becoming stars, becoming galaxies, becoming this magnificent, shimmering architecture. And at every node of that web, at every bright, clustered place where the filaments intersect, there are galaxies, each galaxy a world unto itself. A slow-turning island of light adrift in the great dark ocean of space, and yet none of them truly alone, for the cosmic web connects them all in a structure so vast and so delicate that it resembles, in photographs taken by our most powerful telescopes, each galaxy a world unto itself, a slow-turning island of light adrift in the great dark ocean of space, and yet none of them truly alone. for the cosmic web connects them all in a structure so vast and so delicate that it resembles, in photographs taken by our most powerful telescopes, the inside of something living, something breathing, as though the universe itself has a nervous system strung between the dark and the light. And along those filaments, along those shimmering threads of matter and gravity and ancient momentum, there are places where the story grows particularly rich, particularly warm, particularly bright. Places where the darkness has not won. Places where something extraordinary is always just beginning. Close your eyes for a moment, if you like, and imagine a cloud. Not a cloud above a summer field, not the soft gray wool of an autumn sky, but something almost unimaginably larger, a cloud of gas and dust so immense that it would take light itself thousands of years to cross from one edge to the other. These clouds exist between the stars, drifting in the slow, cold spaces of a galaxy, and they are called nebulae, a word that means mist, a word that means fog, a word that carries within it the sense of something that has not yet decided what it wants to be. And in the language of the universe, these vast and patient clouds of hydrogen and helium and the fine dust of older worlds are nurseries. They are the places where stars are born. It is a quiet process at first. The cloud drifts. It turns, very slowly, over millions of years. And then something disturbs it. Perhaps the shock wave of a distant explosion. Perhaps the gentle gravitational nudge of a passing body, and the cloud begins in some small region of itself to gather. Gravity reaches inward, as it always does, as it cannot help doing, and the gas begins to compress. Slowly at first, then faster still. The material at the center of this collapse draws tighter, grows denser, grows hotter. Pressure builds the way pressure builds inside a clenched fist, the way tension builds before a storm. And the temperature at the core of this collapsing knot of gas climbs higher and higher and higher, through thousands of degrees, through millions of degrees, until something remarkable happens. Until the threshold is crossed, until hydrogen nuclei, moving so fast and pressed so closely together, begin to fuse, begin to join, begin to release the energy locked inside the bonds of matter itself. And in that moment, in that singular moment, when nuclear fusion ignites at the heart of a collapsing cloud, a star is born. There is a warmth to this idea that never quite fades, no matter how many times you return to it. That stars are not simply found in the sky, not simply placed there by some prior arrangement, but made, assembled from raw material, from the simplest stuff in existence, and then lit from within by a process so fundamental that it runs on the same principle as every other source of light and heat and energy in the cosmos. A star is fusion made visible. A star is the universe teaching itself to shine. And once that first light ignites, once that pressure and heat reach the precise balance between gravitational collapse and outward radiation, the star settles into the long, slow rhythm of its life. It begins to burn in the way we use that word for stars, though it is not burning at all in the way a candle burns or a campfire burns. It is converting. At the core, hydrogen becomes helium in a process that releases staggering quantities of energy, and that energy radiates outward, slowly, incredibly slowly, passing through layer after layer of stellar material, bouncing and scattering and being absorbed and re-emitted over timescales that stretch across hundreds of thousands of years before finally, after all that patience, It reaches the surface of the star and escapes into the cold dark of space as light. The light that warms your face on a summer afternoon left the core of our sun a very long time before it reached your skin. It has been traveling through the body of the star itself for perhaps 200,000 years, waiting in a sense for its moment to finally arrive. But here is something that asks you to hold two very different scales in your mind at once, and I want to offer it to you gently, because it is one of those facts that the mind needs a moment to receive. A star's entire life, the full arc from birth to whatever end awaits it, is almost entirely determined by a single quality: its mass. How much of it there is. That is very nearly all that matters. A small star, a red dwarf, a modest, quiet thing burning with a dim and steady redness far below the luminosity of our own sun, can burn for almost incomprehensible lengths of time. Trillions of years, not billions, trillions. The universe itself is only about 13.8 billion years old, and the smallest red dwarf stars have barely begun their lives. They will still be burning when the universe has aged to 100 times its current span, when most of the stories we know from astronomy have long since concluded, when the galaxies themselves have grown sparse and quiet. Red dwarfs will still be there, still converting hydrogen to helium, still shining their dim and patient light into whatever darkness remains. And then there are the giants, the massive stars, the ones that form when particularly dense regions of a nebula collapse, the ones that burn so hot and so brilliantly that they glow blue-white with a ferocity that makes them visible across enormous distances. These stars do not live long. They cannot. Their very size is their undoing, because a massive star burns through its hydrogen with a kind of urgency, a kind of hunger that a smaller star like our sun would never recognize, where our sun will live for about 10 billion years in total. A star 10 times more massive might exhaust its core hydrogen in only a few million years, and a star truly enormous, many tens of times the mass of our sun, might have a lifespan measured in mere millions of years, a cosmic heartbeat, a brief and brilliant flash against the long darkness of time. They are like certain flowers that bloom with extraordinary extravagance and then are gone, their very beauty tied to their brevity, their brightness inseparable from their short time in the light. What happens at the end of a massive star's life is one of the most dramatic events the universe is capable of producing. When the hydrogen at the core runs low, the star begins to fuse helium instead. And when the helium runs low, it fuses carbon, and then neon, and then oxygen, and then silicon. Each element heavier than the last. Each fusion reaction releasing slightly less energy, proceeding slightly faster, until the star is fusing silicon into iron. And iron, in the language of stellar physics, is the end of the road. Iron cannot release energy through fusion. Iron absorbs energy. And when an iron core accumulates at the heart of a massive star, the long negotiation between gravity and radiation pressure comes, suddenly and catastrophically, to an end. The core collapses in less than a second. It collapses so fast and so completely that the outer layers of the star, still falling inward, hit the suddenly rigid surface of the collapsed core and rebound in a shockwave of almost incomprehensible violence. What follows is a supernova, and the numbers involved in a supernova are the kind that require a certain stillness of mind to even begin to receive. In the seconds of a supernova explosion, more energy is released than our sun will emit across its entire 10 billion year lifetime. Read that once more, slowly, in whatever quiet interior space you have available to you. In a few seconds, more energy than our sun produces in 10 billion years. The star does not dim. It does not fade. It detonates. It briefly outshines entire galaxies, entire collections of hundreds of billions of stars, blazing across the dark with a light so intense that it can be seen from the other side of the observable universe. And yet there is something in a supernova that is not destruction alone. There is something in it that asks to be understood as generosity, as completion, because it is in the moments of a supernova, in the extraordinary temperatures and pressures of that detonating core, that the universe makes its heaviest gifts. Hydrogen and helium are made in the Big Bang. Carbon, oxygen, nitrogen, the elements of life, are made inside the cores of stars across their long, quiet lifetimes. But for anything heavier than iron, the universe requires something more violent still. Gold, uranium, iodine, the element without which your thyroid cannot function, without which certain signals in your own body cannot be sent. These elements are not made in the steady burning of a star. They are made in the brief catastrophic fury of a supernova and in the collisions of neutron stars, those extraordinarily dense remnants left behind when a massive star's core collapses but does not quite become a black hole. A neutron star is a thing that deserves a moment of quiet attention, because it represents matter in a state that has no parallel in ordinary experience. When the iron core of a massive star collapses, it collapses so completely that electrons and protons are crushed together into neutrons. And the result is an object perhaps only 20 kilometers across, smaller than many cities on Earth, but containing more mass than our sun. The density involved is beyond anything our daily intuitions are equipped to handle. A teaspoon of neutron star material, just a small spoon of it, would weigh approximately 1 billion tons on Earth. 1 billion tons in a teaspoon. The stuff of a neutron star is so compressed, so impossibly dense, that it represents the very edge of what matter is allowed to be before it crosses into something else entirely. Neutron stars sometimes spin hundreds of times per second, sweeping beams of radiation across space like cosmic lighthouses, and when two of them spiral together and collide, the resulting explosion seeds the surrounding space with gold and platinum and 100 other heavy elements, scattering wealth into the dark. This is where your gold comes from, not from the earth, not in any original sense. The gold in any ring, in any coin, in any gilded thing you have ever held or seen or admired, was forged in a catastrophe that happened before our solar system existed. It was scattered into space by a dying star or a collision of collapsed remnants, and it drifted for millions of years in the cold dark between suns, until it found its way into the cloud of gas and dust that would eventually collapse to form our own star and its family of planets. The gold in the ground beneath your feet arrived here before the Earth existed. It is older than the world, and when you think about this long chain of events, this long, slow process by which the simplest elements in existence are assembled across billions of years, through the lives and deaths of countless stars, into the complex and heavy elements that make chemistry possible and biology possible and consciousness possible. Something shifts in the way the universe feels. It does not feel empty. It does not feel cold. It feels in a quiet and improbable way, purposeful. Not purposeful in the way a plan is purposeful, not aimed at any particular destination, but purposeful in the way a river is purposeful, moving always in the direction that matter and energy and time together require, and leaving behind it, in the slow accumulation of moments, something more elaborate than what existed before. A star lives its life in service of this process, though it knows nothing of service, though it has no knowledge at all. It burns because it must, and it makes heavier elements because the physics of fusion demands it, and it holds its planets in their orbits by the grace of its gravity. And it warms the surfaces of those planets with its outrushing light. And when its time is done, when the fuel is gone and the balance cannot hold, it gives back everything it has ever made, every atom synthesized in its long interior life, every element forged across millions or billions of years of patient nuclear burning, all of it returned to the cloud, to the nebula, to the drifting space between stars, where it will wait sometimes for a very long time until gravity gathers it again and a new star begins to form. A new star, perhaps with new planets, perhaps with new oceans, perhaps with new life, sitting beneath a new sky, looking up and wondering where it all began. And so the story turns on itself, circles back, finds its own beginning in its ending, and its ending in a beginning not yet imagined. The universe does not waste what it has made. The elements do not disappear. They transform. They scatter. They drift. They gather, and they begin again. The iron in your blood was made in the heart of a star. The calcium in your bones was scattered by an explosion so bright it briefly rivaled a galaxy. The iodine that your body cannot do without was forged in a moment of catastrophic collision between two collapsed stellar remnants, spinning toward each other across millions of years before finally meeting in a blaze of gold and fury. You are made of things that have already lived one extraordinary life before finding their way to you. Carry that gently into the night. You're not standing apart from the story of stars. You are a continuation of it. Every breath you take recirculates matter that has passed through the interiors of suns. Every moment of warmth you feel is a reminder that somewhere above you, at a distance of about 150 million kilometers, a star is still burning, still converting hydrogen into helium in its vast and patient core, still holding this small world in its careful gravitational embrace, still sending its light across the empty space between you and itself, so that you might see and be warm and live. Our star is middle-aged now, about halfway through its expected life. It has been burning for about 4.5 billion years and has roughly another 5 billion ahead of it. A span of time so large it dissolves into abstraction, becomes more feeling than number, becomes simply the sense of something that will continue long after every story currently being told has ended and been forgotten. But not all stars have that luxury of time. And not all stars end quietly. Some of them, the giants, the blazing blue-white fires at the upper end of the mass range, burn through their lives with a profligacy that has its own kind of grandeur, spending everything they have in millions of years rather than billions, fusing their way through every element the physics of their interiors allows, element by element, layer by layer, building up within themselves a kind of geological record of their own history, a nested set of shells, each burning a different fuel, until the innermost shell produces iron, and the long conversation between gravity and light finally, inevitably, reaches its conclusion. And when a massive star finally exhausted its last reserves of fuel, it did not simply go dark, but instead gave everything it had ever made back to the universe in a single blinding moment of generosity, scattering iron and calcium and carbon into the drifting clouds from which, billions of years later, and when a massive star finally exhausted its last reserves of fuel. It did not simply go dark, but instead gave everything it had ever made back to the universe in a single blinding moment of generosity, scattering iron and calcium and carbon into the drifting clouds from which, billions of years later, something extraordinary and familiar and impossibly precious would slowly, gently begin to take shape. Imagine, if you can, the patience of it, not the patience of an afternoon or a year or even a human lifetime stretched to its longest possible thread. The patience of deep time, the patience of a universe that has nowhere to be and nothing to prove, that simply allows things to happen in their own unhurried way, folding and unfolding like breath, like sleep. Like the slow turning of a dream you almost remember when you wake. This is the patience that presided over the next chapter of our story. A chapter that feels, somehow, like coming home. It began, as so many beginnings do, with quiet, a vast cloud of gas and dust drifting in one of the spiral arms of our young galaxy. A cloud already rich with the gifts of earlier generations of stars, laced through with hydrogen and helium from the very beginning of time, but also threaded now with heavier elements, carbon and oxygen and silicon and iron, the ashes of stars that had lived and burned and given everything away. Astronomers call this the solar nebula, and for a long time it simply floated, enormous and unhurried, scattered across a region of space so wide that light itself would have taken years to cross from one side to the other. But clouds, even clouds of gas and dust in the cold depths of space, are not immune to disturbance. Perhaps a nearby supernova sent a pressure wave rippling through the nebula, a gentle nudge from the universe, a whisper that said, "Now." Perhaps gravity, ever patient, ever present, simply began to do what gravity always does, drawing matter toward matter, gathering the scattered into the concentrated, coaxing the diffuse and wandering into something more deliberate. Whatever the precise trigger, approximately 4.6 billion years ago, this great cloud began to collapse inward upon itself, slowly at first, then with gathering momentum, the way a sigh deepens into sleep. And as it collapsed, something beautiful happened. The cloud began to spin. This is a consequence of the conservation of angular momentum, one of the universe's most faithful laws. The same principle that causes a figure skater to accelerate when she draws her arms inward. The same principle that governs every pirouette, every spiral staircase, every whirlpool draining slowly from a bathtub on a quiet evening. As the nebula contracted, its rotation quickened, and the spinning caused it to flatten, the way a ball of dough flattens when you spin it between your palms. What had been a roughly spherical cloud became a vast, rotating disk, thin and wide, with most of its mass concentrating at the center. At the center, something extraordinary was being born. The concentration of mass grew denser and hotter, pressure building with each passing millennium, heat accumulating in the collapsing core until, at some threshold moment that no eye had ever witnessed, the temperature and pressure became sufficient to ignite nuclear fusion, and a new star blazed into light. Our sun. Modest by stellar standards, a yellow dwarf of average size and middling temperature, unremarkable in almost every way, and yet to us, to the world, that would eventually drift in the warmth of its light, the most important star in all the cosmos. The sun gathered to itself an almost incomprehensible fraction of what the nebula had contained. When you consider all the mass in our entire solar system, every planet, every moon, every asteroid and comet and drifting grain of dust, the Sun accounts for 99.86% of it. Everything else, all the worlds and smaller bodies we have ever known or discovered, all the landscapes and oceans and ice caps and mountain ranges, represents barely more than 0.1% of the total. The Sun is not merely at the center of the solar system. In a very real sense, the Sun is nearly everything there is. The rest of us, all the planets and their moons, all the small wandering bodies on their long elliptical paths, are made from the leftover crumbs, the trace remainder of a cloud that gave almost all of itself to fire. But what remarkable things those crumbs would become. In the flattened disk of material still surrounding the newly born Sun, the remaining gas and dust began a slower, more intricate process of assembly. Close to the Sun, where the heat was too intense for ice to survive, the lighter volatile materials were driven outward, and only the rocky refractory materials remained, silicates and metals, tiny grains that tumbled and collided in the swirling disk. When two grains drifted close enough to touch, they sometimes stuck together, held by electrostatic forces, the same gentle stickiness that makes dust cling to a surface. These tiny clusters collided with other clusters, growing millimeter by millimeter, centimeter by centimeter, accumulating over thousands and then millions of years into pebbles, then boulders, then objects large enough for their own gravity to draw in more material. The process is called accretion, and it is one of the most patient and persistent forces in planetary science. Slowly, over tens of millions of years, the inner solar system became populated by countless small bodies called planetesimals, each one a candidate for further growth. Each one locked in a slow gravitational conversation with its neighbors. The collisions were not gentle. When two sizable bodies met, the impact was catastrophic by any human measure, releasing energies that would dwarf anything our civilization has ever imagined. And yet, out of collision after collision, out of impact and rebound and merging and shattering and remerging, the rocky inner planets gradually took shape. Mercury, Venus, Earth, Mars, each one assembled from the ruins of smaller worlds, each one a monument to the creative power of destruction. The Earth itself grew over approximately 10 to 20 million years, a blink by cosmic standards, an eternity by any human reckoning. Layer by layer, impact by impact, our world accumulated its mass, its gravity growing stronger with each addition, its interior heating from the energy of all those collisions and from the decay of radioactive elements, until the young Earth was not a cold, solid rock, but a roiling, molten world. Its surface a global ocean of magma, churning slowly beneath a sky thick with volcanic gases and the remnants of a still-clearing disk. And then, approximately 4.5 billion years ago, something happened that would shape our world forever. A body roughly the size of Mars, which scientists have named Theia, was moving through the inner solar system on an orbit that brought it into a slow, inevitable convergence with the early Earth. The collision that followed was not like anything we have words to fully describe. It was an impact so enormous, so total in its consequences, that it did not merely scar the surface of the Earth or leave a crater, but actually disrupted the entire planet, vaporizing much of the impactor and a significant fraction of Earth's outer layers, flinging an enormous plume of molten rock and vapor into orbit around our world. In the hours and days and years that followed, that debris gradually coalesced, drawn together by gravity, slowly cooling and compressing into a new body that settled into a circular orbit and became, in time, our moon. Close your eyes for a moment and try to picture it. The sky of the early Earth, lit from below by the orange glow of a still molten surface, and overhead, enormous, impossibly close, a new moon just beginning to solidify, its own surface still radiating heat from the violence of its creation, hanging in a sky choked with steam and sulfur and the dust of worlds in the process of becoming. There was no life to see it. There were no eyes anywhere in the solar system to witness this astonishing spectacle. But the event itself was real as this moment, as real as the breath you're drawing right now, and it left behind consequences that persist to this day. In the tides that move through Earth's oceans, in the axial tilt that gives us seasons, in the subtle gravitational dance between our world and its companion that has stabilized our climate across billions of years. The moon's presence was a gift, a stabilizing gift. Without it, the Earth might have wobbled chaotically on its axis over geological time, making long-term climates far more extreme and unpredictable than they have been. The moon, born from catastrophe, became one of the quiet guardians of the conditions that would eventually make life possible. But the violence was not over. Not yet. For hundreds of millions of years after the formation of the planets, the solar system remained a more crowded and dangerous place than it is today. The orbits of the giant outer planets, Jupiter and Saturn and the others, were still shifting, still migrating slightly, and those migrations sent gravitational disturbances rippling through the inner solar system, destabilizing the orbits of countless asteroids and comets from the outer reaches and sending them cascading inward. The period from roughly 4.1 to 3.8 billion years ago is sometimes called the Late Heavy Bombardment, and it was a time of extraordinary intensity when the inner planets, including Earth, were pelted by an intense and relentless flux of impactors, asteroids, and comets striking again and again, each one leaving scars that can still be read today in the cratered faces of the Moon and Mars and Mercury. And yet, hidden within this violence, there was something that might be called generosity. Many of those comets and asteroids carried within them water, locked in ices and hydrated minerals, and complex organic molecules, the chemical building blocks from which life might one day construct itself. The bombardment that scarred our world also delivered to it some of the very ingredients from which life would eventually emerge. The universe, it seems, has a way of weaving creation into destruction, of tucking gifts inside catastrophes, of ensuring that even the most violent chapters serve the larger story. Think of this the next time you look at the moon. That familiar face, so pocked and cratered, is a record of an era our Earth has largely erased through its own geological restlessness, through the shifting of tectonic plates and the wearing of wind and water. The moon has preserved what the Earth has forgotten, holding in its silence a memory of the fierce and formative time when our solar system was young and still deciding what it would become. The rocky inner planets settled into their final configurations. The giant outer planets claimed their distant orbits. The remaining debris sorted itself into belts and clouds, the asteroid belt between Mars and Jupiter, the more distant realm of comets still orbiting at the very edges of the sun's gravitational reach. A kind of order emerged from the chaos, not a perfect order, not a still and silent order, but the dynamic, breathing, endlessly interacting order of a system that would persist largely intact. for billions of years to come. And here, at the third rock from the sun, something particular was happening. The Earth, positioned at just the right distance to hold liquid water on its surface, slowly began to change. The bombardment tapered off. The surface cooled. Volcanic gases continued to pour into the atmosphere, but now there was enough stability, enough time between catastrophes for more gradual processes to take hold. Water vapor condensed. The first rains fell on a world that had never known rain before, filling the basins and low places of the cooling crust, gathering in what would eventually become the first oceans. It is extraordinary to realize that the water you have drunk today, the water that moves through your body as you settle towards sleep, was likely delivered to this world during that ancient, violent time, carried here by comets and asteroids from the cold outer reaches of the solar system, or released from the rocks of the Earth itself through volcanic processes that drew on water bound up in the minerals accreted during the planet's formation. The water of your body has been here, in one form or another, for almost as long as the Earth itself. It has been ocean and cloud and ice and river and rain. It has been inside other creatures beyond counting. It has witnessed everything this world has ever experienced. And tonight, it is resting with you, as quiet and ancient and ordinary as sleep. The solar system had arrived, not complete, not finished, for it would continue to evolve and change and be reshaped by forces large and small across the billions of years still to come. But recognizable. The sun burning steadily at the center, the planets moving in their orbits, the moon hanging in the sky above a young and restless Earth, still figuring out what it was going to be. There is something deeply moving about this moment of settling and becoming. This moment when the long journey from the first atoms of hydrogen to a world with oceans and a sky and a moon arrived at something that you might, in a long view, begin to call familiar. The universe had been working toward this for 9 billion years. 9 billion years of stars living and dying, of elements being forged and scattered and gathered again, of gas clouds collapsing and spinning and blazing into light, of debris coalescing around young suns, of impacts and accretions and slow coolings. 9 billion years. And here at last was this particular place, this blue-gray world in the warmth of its yellow star, beginning the next chapter of its long and improbable story. There is a kind of homecoming in it, even if there was no one yet to come home, even if the very concept of home had not yet been invented, had not yet been dreamed or felt or longed for. The conditions for homecoming were being prepared. The stage was being set with extraordinary care and violence and patience and love. If love can be said to operate at the scale of solar systems, and perhaps it can, perhaps the universe's tendency to move always toward greater complexity and connection, and the possibility of experience is a kind of love, slow and vast and impersonal and real. And our young Earth, still glowing from the violence of its own making, slowly cooled beneath skies that no eye had ever seen, oceans gathering in the low places of a restless crust. And somewhere in the quiet depths of those first warm seas, something began to stir that was not quite alive, and yet was no longer quite nothing at all. Something that existed in the liminal space between chemistry and life, between reaction and intention, between the random tumbling of molecules and the slow, astonishing emergence of pattern. It is worth pausing here in this quiet to let that settle over you like the darkness settles over a room at the end of a day. We are speaking of a time so remote that all of human history, All the cities and languages and stories and songs would be a single breath against the long, unhurried exhalation of what came before. The Earth was perhaps 4.5 billion years old when it formed, still wreathed in the afterglow of collision and accretion, and yet within a few 100 million years of that violent birth, within what geologists might call almost immediately, something had already begun. Life, or the precursor of life, or whatever we choose to name that liminal chemistry stirring in the warm and mineral-rich waters of the early ocean, had already found its first tentative foothold on a planet, still learning to be still. 4 billion years ago, perhaps 4.1. The numbers are so large, they lose their meaning unless we try, very gently, to hold them. If you compressed the entire history of Earth into a single year, a human lifetime would occupy less than the final few seconds of December 31st. The first stirrings of life would appear sometime in late January, while the planet was still young and raw and covered in a sky of methane and carbon dioxide and nitrogen, no oxygen to breathe, no blue above, the sun dimmer than we know it now, and yet the oceans present and warm in places and full of the dissolved minerals and organic molecules that had been arriving on meteorites and forming in the chemistry of the early world. And in that strange, ancient warmth, something began to fold itself into meaning. The question of how life began is one of the most profound that science has ever asked, and it remains, in the most wonderful sense, not fully answered. But among the most beautiful and widely supported ideas is what scientists call the RNA world hypothesis, and it invites us to imagine a molecule that was in those earliest days, doing something no molecule had ever quite done before. RNA, ribonucleic acid, is a molecule we still carry in our cells today, still essential, still at work in the translation of genetic information into protein. But in the beginning, the hypothesis suggests RNA may have been working alone and working in a way that was almost paradoxically versatile. You see, most molecules do one thing. A structural molecule holds shape. An enzyme catalyzes reactions. A genetic molecule stores information. But RNA, in its ancient form, appears to have been capable of doing several things at once. It could store information, carrying within its sequence of chemical letters, something like instructions, something like memory. And it could also act as a catalyst, folding back upon itself in intricate shapes and speeding up the very chemical reactions that were necessary for its own continuation. This is a difficult thing to hold in the mind without a sense of quiet wonder. Imagine a sentence that, in the act of being written, also sharpens the pen. Imagine a map that helps build the roads it describes. RNA, in the warm chemistry of the early Earth, may have been something like this: a molecule that encoded its own replication and catalyzed its own survival. Not alive, not yet, not in any sense we would easily recognize, but already doing the thing that life would eventually perfect, the drawing of a boundary between self and not self, the preference of continuation over dissolution, the slow chemical insistence on persisting. From those first RNA molecules, over time, that we cannot really imagine in its vastness, things grew more complex. Membranes formed around clusters of replicating chemistry, creating the first true cells, the first enclosed spaces where reactions could accumulate rather than simply dispersing into the sea. And those first cells, those earliest ancestors of everything that would ever live on Earth, were bacteria and archaea, microorganisms of staggering simplicity and staggering resilience. And they would have this planet almost entirely to themselves for a span of time that dwarfs everything that came after. 3 billion years. Let that settle softly over you as you rest. For approximately 3 billion years, life on Earth meant single-celled organisms, bacteria and archaea, invisible to any eye that did not yet exist, going about their extraordinary chemical lives in the oceans and on the ocean floors and in the sediments and eventually in the thin films of moisture on rocks and shores. No forests, no creatures with faces, no eyes to open or close, no heartbeats, only the patient, relentless, almost incomprehensibly slow transformation of a planet by organisms so small that millions could rest in a space the size of a full stop at the end of a sentence. And yet, quiet as they were, invisible as they were, these microorganisms were doing something enormous. They were changing the world, not intentionally, not with anything like awareness, but with the same inevitability with which water shapes stone, slowly, completely, in ways that would determine everything that came after. They were metabolizing, consuming, producing, cycling the elements of the earth through their bodies and releasing them back transformed. They were, in the deepest sense, geologists, though they did not know it. They were chemists working on a planetary scale over billions of years, and the most dramatic single act in their long tenure on this world came approximately 2.4 billion years ago, in an event we now call the Great Oxidation Event. There is a certain poetry in the fact that what was, for countless organisms, an apocalypse, was also the necessary precondition for everything we think of as complex life. The cyanobacteria, a particular lineage of photosynthetic microorganisms that had evolved the ability to split water molecules and use the energy of sunlight to build organic compounds, were by this point releasing oxygen as a byproduct of their metabolism. Oxygen, which is today so synonymous with life and breath and survival that it is difficult to imagine it as anything else, was at that time a poison. The early atmosphere contained almost none of it. The chemistry of life had evolved in its absence. The rocks and minerals of the ocean and the seafloor had been absorbing what little oxygen the cyanobacteria produced for millions of years, acting as a chemical sponge. And for a long time the balance held. But slowly, the sponge saturated. The iron in the ocean, which had been hungrily binding to oxygen and sinking to the seafloor as iron oxide, the rust-colored banded iron formations we can still see today in ancient rocks, gradually ran out of capacity, and then the oxygen began to accumulate in the atmosphere, and the world changed. Organisms that had never evolved in the presence of this reactive gas found it toxic, and enormous numbers of species were wiped out in what is, by some measures, the largest mass extinction in the history of life on Earth. An extinction caused not by an asteroid, not by a volcanic eruption, not by any sudden violence, but by the patient, cumulative exhalation of billions of tiny organisms going about their lives, never knowing what they were doing to the world around them. It is a strange and slightly vertiginous thought, one that invites a kind of philosophical pause. The cyanobacteria did not intend the apocalypse they created. They were simply living, simply following the chemistry of their existence, and in doing so they transformed the atmosphere of an entire planet and erased most of the life that had preceded them, while simultaneously creating the conditions that would, in time, make possible every animal that has ever drawn breath, including the one resting now, eyes closed, letting these words carry them somewhere between waking and sleep. The oxygen those ancient microorganisms released is the oxygen in your lungs at this very moment. Every breath you take is a gift from an organism that lived 2.5 billion years ago and had no idea you were coming. After the Great Oxidation Event, the world continued its slow, unhurried transformation. The atmosphere now carried oxygen in increasing quantities, and life adapted, as life always does, bending itself to the new chemistry of the world, finding new ways to use this reactive molecule rather than simply being destroyed by it. And the Earth moved on through its deep time, through the slow dance of continents drifting and colliding, through ice ages that may have frozen the planet nearly to its equator in the episodes geologists call Snowball Earth, through the quiet accumulation of ecological complexity in the oceans, one patient innovation building on another. Nothing hurrying, nothing straining toward a destination, only the endless experimentation of chemistry and time. And then, approximately 1.5 billion years ago, something happened that was so improbable, so strange, so unlike anything that had come before, that it deserves to be described with a kind of reverence. A large cell, one of the ancestors of what we now call eukaryotes, the domain of life that includes every plant and animal and fungus that has ever existed, engulfed a smaller bacterial cell. This was not in itself unusual. Cells engulf other cells. It is a common enough event in the microbial world, a way of taking in nutrients, a form of predation at the smallest possible scale. But this time, for reasons we can only imagine, the smaller cell was not digested. It survived inside the larger one, and the two, over millions of years, reached a kind of accommodation, a partnership so deep and so thorough that we no longer speak of them as separate organisms at all, but as organelles and cells, as parts of a single integrated whole. The smaller cell became what we now call the mitochondrion, and the evidence for this ancient partnership is written in the biology of every complex cell on Earth. Mitochondria still have their own membranes, a remnant of their life as free-swimming bacteria. They still divide by binary fission, the way bacteria divide, not by the mechanisms used by the rest of the cell. And most remarkably, they still carry their own genome, their own small circle of DNA, encoding a handful of genes that were never fully absorbed into the nucleus of the cell that engulfed them. You can sequence the mitochondrial genome right now and find it is unmistakably bacterial in character, a remnant of a life lived freely in the ancient ocean, before the agreement was made, before the merger occurred, before two organisms became one in a partnership that would eventually make possible every complex life form on this planet. This is the endosymbiotic theory, and it is one of the most beautiful and well-supported ideas in all of biology. It tells us that inside every cell of your body, there is an ancient stranger, something that was once its own creature, with its own lineage, its own evolutionary history stretching back to the oxygen-rich aftermath of the Great Oxidation Event and beyond. The mitochondria in your cells are not you. Exactly. And yet they are completely you, completely essential to your life, completely woven into the fabric of your biology. They are the power sources of your cells, converting the oxygen you breathe and the food you eat into the chemical energy your cells use for everything. For thought and movement and the slow repair of tissue while you sleep. They are doing this right now, in the quiet of your rest, in every cell of your body, without your awareness or your direction, as they have been doing since long before anything like you existed. The story of life on Earth is a story of patience on a scale that is almost impossible to hold in a human mind, which is accustomed to the pace of days and seasons and lifetimes. It is the story of 4 billion years of chemistry becoming biology, of single cells discovering how to cooperate and eventually merge, of an atmosphere being slowly transformed by the accumulated breath of invisible organisms, of the same carbon and oxygen and nitrogen cycling and recycling through body after body, through species that rose and flourished and vanished and were replaced, through extinctions and radiations and ice and warmth and the slow drift of continents, all without haste, all without anyone watching, all in the dark patience of deep time. And we who have existed for the thinnest imaginable sliver of that time carry the whole of it within us, in our cells, in our molecules, in the ancient bacterial heritage of the very structures that keep us alive. It is a strange and humbling thought that the very mitochondria working quietly within every cell of your body as you rest now carry their own separate ancient lineage, their own remnant genome, whispering of a time when they were free-swimming creatures in a world that had not yet imagined anything as complicated and luminous as what was coming. Rest with that for a moment. You are carrying within you the memory of a world before memory. You are made of collaborations so ancient they predate the very concept of collaboration. And from that deep, patient foundation, something was about to stir. For billions of years, the story of life on Earth had been a quiet one. Microscopic, chemical, slow. The oceans were full of life, yes, but it was life that did not see, did not reach, did not move with intention across great distances. Single cells drifting in the ancient dark water. Mats of bacteria lying across shallow seafloors, breathing and dividing and being, but not yet becoming anything that would recognize itself in a mirror. And then, somewhere around 538 million years ago, something shifted. Not suddenly, not in the way we sometimes imagine explosions to happen, but quickly by the patient timescale of geology. Quickly in the way that a held breath is released after an enormously long time of waiting. We call it the Cambrian explosion. Though explosion is perhaps too violent a word for something so astonishing and tender. Over a span of roughly 20 million years, which sounds long to us but is barely a heartbeat in geological time, the seas of Earth became populated with an extraordinary diversity of animal body plans. Creatures with eyes and legs and grasping appendages. Creatures with shells and spines and segmented bodies. Creatures that swam and crawled and burrowed. Creatures that filtered the water and creatures that hunted other creatures. Suddenly, in the fossil record, the world goes from being largely simple and microbial to being populated with forms we can almost recognize. The major architectures of animal life, the blueprints that would eventually give rise to fish and worms and insects and distantly, to you, appear in the rock in this one remarkable flourishing. No one knows entirely why. The ocean chemistry was changing. Oxygen levels were rising, making more energy available for complex and hungry bodies. Predators emerged, and with predators came the urgent evolutionary pressure to develop defenses, and with defenses came the arms race of complexity. Some scientists believe that the evolution of the eye itself was a kind of trigger, a discovery so powerful and useful that it reshaped the entire web of life almost overnight. Imagine what it meant to see. Before eyes, the world was experienced in gradients of chemistry, in touch, in vibration, in the slow negotiation of molecules. Then, suddenly, some creature developed a simple patch of photosensitive cells, and light itself became information. Vision turned out to be such a good solution to the challenge of navigating a light-filled world that it evolved not once, not twice, but at least 40 separate times across completely different lineages. 40 independent discoveries of the same astonishing gift. The fly and the squid and the human being each arrived at the eye through different genetic pathways, different ancestral starting points, different millions of years of trial and experimentation. And yet something so similar emerged from all that divergent journeying. It is as if the universe had a direction it was leaning toward, a set of solutions it kept returning to, not because anything planned it, but because light is real and eyes that gather light work, and working is rewarded by survival. The world shaped the creatures that could perceive the world, and perceiving the world, those creatures shaped themselves and each other in return. Picture it, if you can, drifting into sleep. This ancient sea, not the cold black void we sometimes imagine when we think of deep time, but a living, moving, shimmering world. Soft-bodied creatures trailing through warm, shallow water. Strange architectures of life that have no exact equivalent today. Experiments that would not be continued. Body plans that time would eventually set aside. And among them, the first glimmers of directed perception. The first faint ancestors of awareness. Eyes that could not yet wonder at what they saw, but that could detect a shadow, could respond to a moving shape, could distinguish the faint brightness above from the dark below. That was enough. That was, in its way, everything. The story moves forward now, as all stories do, through an almost incomprehensible succession of generations. Life moved out of the seas and onto the land. A transition so improbable and so demanding that it is almost impossible to imagine the courage of it, except that there was no courage. Only physics and chemistry and the blind insistence of genes replicating themselves through whatever bodies could be built. Fish grew limbs. Amphibians crept onto muddy shores. Reptiles developed eggs that could survive away from water. Forests arose and burned and arose again. Continents drifted. Ice ages came and retreated like long, slow tides. The dinosaurs walked the earth for so long that the entire span of human civilization is invisible against their tenure, a single breath against a century of breathing. And through it all, within the lineage that would eventually become yours, something was quietly elaborating. The nervous system, that ancient and elegant solution to the problem of coordinating a body in a changing world, was deepening, folding, becoming more intricate, more layered, more capable of holding within itself not just reflexes and responses, but something that begins to look, in its increasing complexity, like experience, like interiority, like the faint first suggestions of a within. By the time the first small mammals scurried through the underbrush in the shadow of enormous reptiles, the basic architecture of what would become the human brain was already beginning to take shape across those millions of quiet generations. And then, in the great reset of the asteroid impact 66 million years ago, when the sky went dark and the great reptiles disappeared, the mammals inherited an emptied world and filled it with themselves, diversifying into every niche, growing larger, growing more complex. The brain elaborating itself in one lineage after another with particular and extraordinary ambition. 300,000 years ago, on a continent that we now call Africa, a species appeared that carried within its skull something unprecedented. We call them Homo sapiens, and we are them, and they are us. And there is a deep and gentle strangeness in that fact that it is worth sitting with in the quiet dark before sleep. 300,000 years ago, creatures with essentially your body, essentially your brain, essentially your face and your hands and your capacity for language, were walking across the grasslands of Africa beneath the same stars that drift above you tonight. And yet, for a long time, something was still settling. Something was still finding its fullest expression. The archaeological record suggests that behaviorally modern humans, those who were making art, leaving symbols, demonstrating the full flowering of that strange capacity for complex language and abstract thought and the rich inner world of meaning and story, appear clearly only between 100,000 and 70,000 years ago. For 200,000 years, perhaps, people carried the architecture without fully inhabiting every room. And then, gradually or suddenly, something woke. We do not know exactly what changed. Perhaps it was a refinement in the connections between regions of the brain that allowed language and memory and imagination to begin to speak to each other in new ways. Perhaps it was a cultural threshold, one discovery leading to another in a cascade. Perhaps it was simply that a certain density of connection within communities created the conditions for something new to emerge, the way that a network of simple elements, when it becomes complex enough, begins to exhibit behaviors that none of its individual parts possess. Whatever the cause, the evidence is unmistakable. Ochre paintings on cave walls, beads strung on cord, burials with flowers and objects that suggest a belief in something beyond the moment of death. Music, almost certainly, though music leaves no fossil. Story without question. Because story is the water that the human mind swims in, and we have been swimming in it ever since. Inside the skull that carried all of this was, and is, a structure of almost incomprehensible intricacy. The human brain contains approximately 86 billion neurons, each one a living cell that spends its days and nights firing tiny electrical signals through its branching extensions, communicating with its neighbors across gaps called synapses. Each neuron forms on average around 7,000 synaptic connections with other neurons. When you do the arithmetic, quietly and without rushing, you arrive at a number somewhere in the neighborhood of 100 trillion connections. 100 trillion. The stars in the Milky Way number only in the hundreds of billions. The connections in a single human brain outcount the stars in our galaxy by a factor of hundreds. And somehow, from the particular patterns of activation flowing through that vast and intimate web, from the precise cascade of signal and response moving through that living network folded inside the darkness of your skull, something arises that we call experience. Something arises that we call you. This is where science pauses in something very much like humility, because we do not understand it. Not really. We can map the brain with increasing precision. We can watch regions illuminate in colorful scans when you feel fear or love or curiosity. We can trace the pathways of sensation and thought and memory through that extraordinary web, but we cannot explain why any of it feels like anything. Why the firing of neurons is accompanied by the warmth of sunlight on skin, by the ache of missing someone, by the particular blue of a morning sky that catches your breath without warning. The presence of subjective experience, the fact that there is something it is like to be you, remains one of the deepest unsolved problems in all of science. Philosophers and neuroscientists call it the hard problem. And hard is perhaps the most elegant understatement in the history of human inquiry. We do not yet understand why physical processes give rise to subjective experience. We do not know how the lights came on inside, but they did come on. And here you are, lying in the kind dark, breathing slowly, your 100 trillion connections humming their soft electrical music, carrying in this moment the full weight and wonder of everything that led to this. Stars that burned and collapsed, gas clouds that found their way into suns, planets that cooled and pooled their water into seas, cells that merged and persisted, eyes that opened onto the light, brains that grew and folded and deepened until they could hold within themselves not just the present moment, but the distant past and the imagined future, not just the self, but the idea of the self, not just the world, but the astonishment of being in it. 4 billion years of life, building carefully on itself, each generation inheriting the experiments of all the ones before, each nervous system a little more elaborate than the last, each new layer of connection, adding some further dimension to what it might mean to be alive. And at the end of that long, patient, beautiful, unspooling, you, aware, wondering, capable of lying still in the dark and feeling something you might only be able to call tenderness toward the improbable fact of your own existence. The universe spent 13 billion years becoming a place where such tenderness was possible, and perhaps the most remarkable thing of all is not the complexity of the eye, or the vastness of the neural web humming inside a human skull, but the quiet fact that the universe, after 13 billion years of patient labor, had finally arranged matter in such a way that matter could look back at itself and wonder. To know, to ask, to lie awake beneath a canopy of stars and feel something that has no name in the language of physics, something closer to awe or tenderness, or the strange vertigo of realizing you are the universe becoming briefly aware of its own immensity. And what an immensity it is. Close your eyes now if you like, and let the numbers come gently, the way water comes to the shore, not crashing, but arriving, one soft edge at a time. Because the story we are about to follow does not belong to any single lifetime, or any civilization, or even any star. It belongs to time itself, stretched out so far beyond our ordinary reckoning that the word future begins to lose its familiar shape and becomes something else entirely. Something vast, something still, something that asks nothing of you except the willingness to rest inside it. We begin where we are. Here, in this particular moment, in this particular universe, which is approximately 13.8 billion years old, it has been busy, this universe. It made hydrogen, and from hydrogen, it made stars, and from stars, it made everything heavier. The carbon in your bones, the iron in your blood, the calcium pressed quietly inside each tooth. It made galaxies by the hundreds of billions, each one a slow wheel of light turning through the dark, and it filled the space between them with something we can feel but cannot see. Something physicists call dark energy, which is not dark in the sinister sense, but simply invisible to our instruments, present everywhere and nowhere, woven into the very fabric of space like a breath held indefinitely. Dark energy is strange and patient and everywhere. It constitutes approximately 68% of the total energy content of the universe, more than all the stars, all the gas, all the mysterious dark matter swirling through galactic halos. Most of what the universe is made of, we cannot touch or taste or name with any confidence. We only know it is there because of what it does, And what it does is this: it pushes. Quietly, persistently, without urgency or drama. Dark energy causes the universe to expand, and not just to expand, but to expand faster and faster, so that the space between galaxies is stretching like warm dough pulled gently from both ends, and the light from distant things is being slowly carried away. Even now, as you breathe here in the dark, there are galaxies receding from us so quickly that their light will never reach us again. They are crossing a kind of horizon, not a physical wall, but a boundary written in the mathematics of acceleration, beyond which no message, no photon, no signal of any kind can make the journey home. The universe is, in this quiet sense, already forgetting pieces of itself, letting them go, watching them drift beyond the last edge of what can be seen or known. And there is something in this that feels less like loss than like release, the way sleep itself lets go of the day, detail by detail, until only the essential warmth remains. In approximately 5 billion years, our own sun will reach a turning point. It has been burning hydrogen in its core since before the Earth existed, fusing atoms together in the relentless solar furnace, and one day, one long, slow, geological day, measured in billions of years, it will exhaust that hydrogen. When it does, it will not go quietly. The sun will swell, growing larger and redder and stranger, expanding into what astronomers call a red giant, a swollen luminous sphere that will reach outward past the orbit of Mercury, past the orbit of Venus, and possibly, perhaps, past the orbit of Earth itself. The inner planets will be consumed or scorched beyond recognition. The oceans of Earth, if any trace of them remains by then, will have long since boiled away. Life as we know it will have moved, or ended, or transformed into something we could not recognize from here. But even this, enormous as it seems, is only a chapter. The sun's red giant phase is a brief dramatic flourish in a much longer story. After the swelling comes the collapse. Not a violent explosion like a massive star's death, but a quieter ending. The outer layers will drift away into the surrounding space, forming a glowing cloud of gas and dust, a planetary nebula, beautiful and temporary, illuminated from within by what remains, a small, dense, incredibly hot remnant called a white dwarf, no larger than the Earth, but containing the mass of a sun. A cooling ember, a memory of fire, slowly fading over billions of years into dimness, then darkness, then a cold object drifting through an increasingly empty universe. And the universe, all this time, continues expanding. Galaxies that are gravitationally bound together, like the Milky Way and Andromeda, and the local group of galaxies clustered around us, will remain bound, will eventually merge into one vast, diffuse elliptical cloud of old stars. But beyond the local group, all other galaxies will recede, one by one, beyond the observable horizon, until the sky, as seen from any world within our local cluster, contains almost nothing but darkness. The brilliant panorama of hundreds of billions of galaxies we can see today will, in the far future, be invisible, not destroyed, but simply beyond reach, beyond light, beyond all possible communication. Imagine lying beneath that future sky. No Milky Way arc, no smudge of Andromeda, no distant spirals catalogued by ancient astronomers. Just the slow turning of a few old stars in a merged and fading galaxy, and beyond them, an ocean of darkness so complete that the universe might seem, to anyone living then, to be almost entirely empty. They would not be wrong, but neither would they know what had come before, The brilliant, crowded epoch of stars and light that we inhabit right now, this extraordinary, almost improbably luminous moment in cosmic history. The stars themselves will continue to die, one by one. The most massive ones burn fast and bright and end in spectacular supernovae. The smaller ones burn slowly, quietly, for tens of billions of years. The very smallest, the red dwarf stars, barely more than glowing coals by stellar standards, may last for trillions of years. A trillion years, a number that makes the current age of the universe seem like the first note of a very long song. And yet even those patient red dwarfs will exhaust their fuel in time. Even they will cool and dim and become cold, dark objects, turning slowly through empty space. What comes after the last stars? A universe of remnants, white dwarfs cooling toward absolute zero. Neutron stars, the ultra-dense cores left behind by supernova explosions, slowly radiating their last heat into the void. Black holes, the most dramatic endpoints, the places where matter has collapsed so completely that not even light can escape, persisting longest of all. Their gravity gathering whatever sparse matter still drifts nearby, growing slowly, waiting, on timescales almost too long to hold in the mind. Even the black holes will end. There is a process theoretical and gentle and strange called Hawking radiation. Stephen Hawking predicted that black holes are not perfectly black, that at their edges quantum effects allow tiny amounts of energy to slowly leak away, particle by particle, over timescales of extraordinary duration. A stellar mass black hole, the remnant of a star several times larger than our sun, would take roughly 10 to the power of 100 years to evaporate completely through this process. 10 to the 100th power. Written out, that number is a 1 followed by 100 zeros, and it is so much larger than the current age of the universe that comparing them is like comparing the width of a single atom to the distance across the observable cosmos. The universe is roughly 10 billion years old, give or take. 10 to the 100th power years is the time scale for the last black holes to finally quietly dissolve. These are not numbers for anxiety. These are numbers for something closer to wonder or rest. And after the last black hole evaporates, the particles it releases will drift apart in an expanding universe, growing cooler and more diffuse with every passing eon. There will be no more concentration of energy sufficient to drive any process, any reaction, any motion of the kind we associate with time's arrow. The universe will have reached a state that physicists call maximum entropy, sometimes named the heat death, sometimes the big freeze, not cold in the way a winter morning is cold, but cold in the absolute sense, a uniform stillness, a democracy of temperature in which every point in space is as warm or as cool as every other, in which there is no gradient left, no difference left, no river of energy flowing from here to there to power any star or cell or thought. This is the heat death. It sounds perhaps like something sorrowful, but consider it gently, the way you might consider the surface of a still lake at dawn. Maximum entropy is not destruction. It is completion. It is the universe having used everything it had, having converted all its magnificent structured energy into the most diffuse, most equitable, most evenly distributed form possible. Every atom will still be there. Nothing will have been lost, only spread, only quieted. And even this may not be the final word, because the observable universe, the The sphere of space from which light has had time to reach us since the Big Bang is only a tiny, almost vanishingly small region of what may be an infinite or near-infinite cosmos. Theories of eternal inflation suggest that our Big Bang, the event that started all of this, that ignited 13.8 billion years of stars and matter and life and consciousness, was not unique, may not have been unique, may have been one of countless such events occurring in a vast and ongoing multiverse, a sea of possibility in which bubble universes nucleate and expand and evolve, each one a separate cosmos with its own laws, its own constants, its own version of time. In this picture, the heat death of our universe is not the end of everything, but merely the local quiet, the particular evening of this particular universe, in a larger story we cannot see from here. There is no way to confirm this. The other universes, if they exist, are beyond any horizon we could ever cross, beyond any signal we could ever send or receive. But there is something in the idea that feels like a great exhale. The notion that creation is not a single candle burning down to nothing, but something more like a field of candles or a sky full of them, each one lit at a different moment. Each one burning in its own darkness, each one briefly warm, and yet there is something deeply restful in contemplating those unimaginable distances of future time, in knowing that the universe does not rush, that it has never rushed, that every star and stone and sleeping creature has always been carried forward on the same unhurried current, the same patient expansion that began when, and yet there is something deeply restful in contemplating those unimaginable distances of future time, in knowing that the universe does not rush, that it has never rushed, that every star and stone and sleeping creature has always been carried forward on the same unhurried current, the same patient expansion that began when everything that exists was smaller than a thought, smaller than a breath, smaller than the pause between one heartbeat and the next. And from that unimaginable compression came all of this, came you, came the particular arrangement of atoms that right now is breathing slowly in the dark, settling into rest, becoming a little heavier with each exhale, a little more at home in the soft gravity of this moment. There is something I want you to hold gently as you drift, something quiet and true and almost too tender to say aloud. You are not separate from the universe contemplating itself from the outside. You are the universe, turned inward, looking at its own hands, feeling its own warmth, wondering at its own existence in the particular and unrepeatable way that only you can wonder. Every question you have ever asked about the stars, every night you have ever looked up and felt that sweet vertigo of smallness, every moment of awe or longing or simple quiet joy. These were the cosmos experiencing itself through the instrument of you, and there is no more extraordinary thing anywhere in the known universe than that. Consider your bones for a moment, not as a medical fact, not as biology, but as a story. The calcium that gives them their quiet strength, that holds you upright through every day of your life, was not made here. It was not made in any furnace that human hands have built. It was forged in the nuclear heart of a star so ancient that our own sun did not yet exist. A star that burned for millions of years, and then, in its final act, gave everything outward in a single catastrophic blossoming of light and matter, scattering the elements of itself across the surrounding darkness. That calcium drifted through the cold of interstellar space. It gathered slowly into clouds. It fell, with everything else, into the condensing disk of material that would become our solar system, that would become our Earth, that would become the ancient seas. That would become the earliest single-celled life clinging to the edges of volcanic vents in darkness that would become over billions of patient years of transformation and inheritance and change. The particular lineage of living things that eventually, improbably, beautifully, led to you. Your bones are the autobiography of a dead star. They carry its story inside them right now. And every breath you take is held up by starfire that predates the sun. And then there is your blood, and the iron it carries, and the deeper and stranger story that iron tells. Because the calcium in your bones came from a single dying star. But the iron in your blood is older and more violent and more romantic than even that. Iron of the kind that runs through living things. Iron that carries oxygen from your lungs to every cell of your body. Iron that right now is moving through the chambers of your heart in the quiet rhythm of sleep. This iron was forged not in any single star, but in catastrophe beyond imagining. In the collision of neutron stars, the densest objects in the universe, stars so compressed that a teaspoon of their material would weigh more than a mountain. Stars that spiraled toward each other across millions of years and then met in a violent merger so energetic that it briefly outshone entire galaxies, releasing in that single moment more heavy elements than our sun will produce in its entire lifetime. The iron in your blood is a relic of such a collision, occurring in some distant region of the galaxy billions of years before our world existed. It traveled through space, through time, through the slow architecture of chemistry and geology and evolution, and it arrived at last here, inside you, doing the quiet and essential work of keeping you alive. You carry the aftermath of colliding stars in your veins, and right now, as you rest, that ancient iron is still working, still moving, still faithful to its task. And the water in your body has a history so long and so winding that it makes the mind go soft and dreamy just to trace the edges of it. Each water molecule you carry, and your body is mostly water, mostly this ancient and patient substance, has been on a journey of billions of years. Those molecules have been part of glaciers, have been locked in ice for millions of years at a time, have been lifted by sunlight into clouds and fallen as rain onto mountain ranges that no longer exist, have moved through rivers that carved canyons, have passed through the bodies of creatures so ancient they have no names we know, have been drunk by dinosaurs and exhaled by ferns and frozen into comets and carried to Earth from the distant cold of the early solar system. The water in you is not yours alone. It has never belonged to anyone. It has always been passing through, on its way from one form to another, and right now it rests inside you the way a river rests in a lake, temporarily gathered, temporarily still, before it moves on again to become something else equally astonishing. You exist in a particular moment of cosmic time that has a name. Cosmologists call it the Stelliferous Era, which means in the most literal sense the age of star-bearing, the time when the universe is rich with stars, when galaxies blaze with nuclear light, when the conditions exist for planets and oceans and life and minds looking upward at the night sky. This era will last for approximately 100 trillion years from the beginning of the universe, which means that in the vast accounting of cosmic time, we are still early, still in what you might think of as the brilliant morning of the universe's long life, still inside the window when everything is lit from within, when stars are being born and living out their long, slow lives and giving their substance back to the galaxy to be reborn as new stars, new worlds, new possibilities. 100 trillion years is a span of time so large that our human minds cannot hold it, can only gesture toward it the way you might gesture toward the horizon. Knowing it extends beyond what you can see, and you, in this moment, are alive inside that golden era, inside that luminous window, at a time when the universe is still young enough to be burning brightly in every direction. There is something unutterably precious in that, something worth carrying quietly into sleep. And then there is perhaps the strangest and most ghostly gift of all, the one happening to you right now without your knowing, without your feeling, without any sensation whatsoever. Right now, as your body rests, as your breathing slows and your thoughts begin to soften at their edges, you are being passed through by neutrinos. Approximately 336 of them pass through every cubic centimeter of your body every second. And these are not neutrinos from the sun, not neutrinos from the nuclear reactions of nearby stars, though those are passing through you too in their billions, also silently, also without touching you. These particular neutrinos are older than the Earth. They are older than the solar system. They are older than any star that is currently burning in the sky. These neutrinos were produced in the first moments of the universe, in the first second after the Big Bang, when everything that exists was unimaginably hot and dense and alive with the first interactions of matter and energy. They have been traveling ever since, cooling as the universe expanded around them, spreading outward for nearly 14 billion years, passing through everything, touching nothing, carrying within them the faintest and most ancient signature of the very first moment of creation. And right now, they are passing through you, these ghosts of the beginning, these messengers from a time before stars existed, before space had expanded enough for light to travel freely, before anything we would recognize as the universe had taken shape. They pass through you the way memory passes through sleep, without weight, without friction, leaving no mark, touching everything. It is a remarkable thing to be the kind of creature that can know this, to be assembled from the remnants of dead stars and ancient collisions and the long cycling of water through time, and to be able to lie in the dark and understand, however dimly, however imperfectly, the story of where all of it came from. The understanding itself is perhaps the most astonishing part. Not the calcium, not the iron, not the water, not the neutrinos streaming through without pause, but the awareness that can hold all of this lightly, that can feel the weight of deep time and be moved by it rather than crushed by it, that can find something like comfort in the knowledge of how small and how brief and how impossibly rare this moment is. Because here's what I want you to feel, or rather to let yourself remember, the way you remember things in that soft borderland before sleep, where knowing and feeling become the same thing. You have always been here, not you in this particular form, not this name and this body and this life, but the stuff of you, the ancient matter that temporarily calls itself you, has been part of this universe from the very beginning, has been present in every transformation, has ridden every wave of change from the first moments of creation through the long dark of the pre-stellar era, to the ignition of the first stars, to the slow building of galaxies, to the explosive death of the stars that made your calcium, to the ancient collision that made your iron, to the condensation of the cloud that became your sun, to the slow cooling of the world that became your earth, to the first stirring of life, to the long patient work of evolution, to the lineage that led to the hands now resting still, to the breath now quiet, to the mind now finally, gratefully letting go. You have always been on your way here. And here is simply wherever you are right now in this moment, with the sheets warm around you and the room dark and the sounds of the world growing softer, more distant, more like the sound of a river heard from a great and comfortable way away. The universe has been arranging itself for nearly 14 billion years to arrive at this configuration, at this particular distribution of atoms and energy and awareness. And there is nothing it needs from you tonight except exactly what you're already doing, which is resting, which is breathing, which is releasing the day back to the dark, like releasing a held breath, like setting down something you have been carrying a long way without knowing its weight until now. The neutrinos are still passing through you, uncountable and ancient, connecting you without your knowing to the very first instant of time. The iron in your blood is still moving, still quietly faithful, carrying its starborn oxygen from one cell to another in the slow rhythm of sleep. The calcium of old dead stars holds you gently in the shape of you. The water rests inside you, gathered and still for now, dreaming its own long dream of glaciers and clouds and ancient seas. And the universe continues its unhurried expansion outward in every direction, carrying all of this forward on the same patient current it has always used. The same current that carries sleeping children and distant galaxies and the light of stars that burned out before the Earth existed, all of it moving together, all of it held, all of it luminous in its own quiet way. The way you are luminous right now in the dark, warm and breathing and briefly, miraculously here. And so we rest here cradled at the end of 13 billion years of starlight and silence. This journey through the deep and ancient universe is gently complete now. When you're ready, another chapter waits softly ahead. But for this moment, simply breathe. Let the cosmos hold you and drift wherever sleep carries you. Good night, dear one. You are loved beyond measure.